Just we know which one to open. There's always someone else going to I know one of the guys, the other guy usually takes a photograph. Is there any number you need there to know?
Okay. Well, I'll get him the word.
Do you know when will be the 3660 the flight simulation stuff with King? Yeah, I know it's quite interrupted. You are maybe too tired to do it.
No, I don't know when. When I have time, I will do it.
Well, like this week or next week?
Oh, it has to be this week because once you start on Monday.
Also, like at the weekend, maybe.
Well, okay, let's do it this way. Either today or Sunday.
Or today or Sunday.
Saturday.
Okay, I will kill an eye.
I'm too tired, too busy on Saturday. I won't do anything.
Oh, okay.
Okay. Good morning. This is a rather usual sight for the morning after a test that the attendance is not very high. But I still don't know. I should probably run a survey. Are you guys the ones who did well and you feel good about the subject, so you like to come? Or are you maybe those who didn't do well and now you are trying to make up for what you missed? And I guess I'll never find out. So what is a transfer function of an integrator? what do we have in here? Remember, in the S domain, this would be X of S. And this would be what? Laplace transform of an integral okay. Laplace of an integral is 1 over S. Maybe you are the other group of people, okay? If you don't remember integral, Laplace transform integral. Or maybe you're just too tired from partying all night last night, celebrating good test. Okay, so if this is the input, this is the output, transfer function G of S equals to output, which is 1 over S X of S, over input, which is X of S. Cancel this and this, so it is 1 over S. So the transfer function is 1 over S. So an integrator is 1 over S. Okay, so now lecture 6. This introduction is important. Again, we need to remember once again that in the S domain, transfer function times input is the output. So the signal coming into this block will be actually multiplied by whatever is in the block. So the output is a multiplication, a product of the input and the transfer function. Now, lecture 6 is about a new way of creating a transfer function of a more complex system. So you know what we were doing so far, especially in the modeling part, lecture 3, 4, and 5. We would get a system and try to break it into individual components, write differential equations describing each of those components, and then manipulate those equations to eliminate the variables we don't need, the intermediate variables, in order to end up with one differential equation with only input and output variables and their derivatives. And some people, probably most of you, sometimes find that extremely tedious and prone to errors. Especially when I was visiting one of the tutorial groups and someone was complaining about that plastic molding or plastic squeezing mechanism where you have a lever, where you have 3 displacements, where you have 2 springs, a damper, plastic acting as a damper. I forgot, it said 3, I just forgot which problem was it, 8 or 9. So, and someone asked me, well, there are a lot of equations we have to write, and now it takes a long time until we get the differential equation we want. That's true. So this lecture is about an alternative method where you don't have to spend too much time manipulating those differential equations in order to get the mathematical model of your system, in order to get one differential equation. So this is called the block diagram method. But still, there are some rules and some tricks to be remembered or to be learned. Okay, so this is something I started with, just in case you forgot, a differentiator. We'll have a transfer function S. An integrator will have a transfer function 1 over S. So when creating a block diagram, you will see very often we will have integrations. A little bit less often we'll have differentiations. So this is what we are going to put into those little boxes. Block diagram technique is there is nothing really theoretical there. So we'll start straight with an example. And we'll go through a number of examples, practical, real systems. And we'll try to create transfer functions by using this block diagram technique rather than, as I said, manipulating differential equations. And we'll start with a well-known system we are all familiar with, a mass spring damper system. And we want to derive the transfer function, but not the way we have done so far. We know now how to do it. But we are going to use the block diagram approach. So through this system, we are going to learn the first few things about block diagrams. OK, so you have a mass. Input variable is this force Fi. Output is x. So when you apply a force, mass will move by x. However, as the force is applied downwards, you will have both spring and the damper opposing the motion. So two forces upwards will be generated as a result. And the algebraic sum of those three forces will be equal to inertia, mx double dot. What you start, or I suggest you start, with what we call a summation point, which is simply a circuit. Some people, like this gentleman here, they like to put a sigma, letter sigma inside to indicate, to re-emphasize it is a summation. I usually just leave an empty circle because we know it is summation. And then there are arrows pointing towards the circle. Those are different terms in the sum. And one arrow pointing out of the circle, that is the result of the sum. Mx double dot, that's inertia. And it is equal to, as we said, the sum of all other forces. It is Fi minus the spring force minus the damper force. So this is the first step. Now, from this point onwards, you start thinking, OK, Fi is my input, so I'm quite happy to have Fi coming from the right to clearly indicate it is the input to this system. But what should be on the left, the arrow pointing out of the system, it's x, displacement x. Over here, I don't have x. I have mx double dot. OK. So what I want to do is somehow create x out of mx double dot, or in the S domain, ms squared x. So what I'm going to do, I'm going to divide this signal here by m, or multiply by 1 over m. So over here, the output of this single box here is s squared x, or x double dot. Then I will put an integrator. That means I will get rid of one s, so I have sx. And another integrator gives me x. Now try to remember the last three. Am I yelling too much? The last three don't really exist. When you look into this system, you can't see an integrator. You can't see a division by m. So that's what we are doing in order to complete a block diagram of this particular system. Okay. Now, this is still not finished. So yes, we have our input coming from the left. Yes, we have our output leaving the system on the right. But we still have two more inputs, showing here, these two arrows, that don't exist here. Here you have only one input. So what do we do here? If this is supposed to be k times x, and here I have x, I will take that signal back, multiply by k, and bring it here to connect with this arrow. We call it a feedback loop, by the way. By this stage, just follow that. So taking x back, multiplied by k, and bring it here. That's what we have down here on this picture. Also, over here we have Cx dot, or CSX. So we go here, where Cx dot already exists, take that signal back, multiply by C, and take it, connect with this arrow here. Now, this is a complete block diagram of the system. So you see, you have the input, you have the output. What is in between is where our transfer function is hidden. So our transfer function is somewhere here. So this is how you build the block diagram. This is a very useful method when you are simulating different systems. And there are different kinds of software that do simulation that rely actually on block diagram technique. One is Simulink, part of MATLAB. They actually use this approach. Or if you use Simulink, you can build a system using these little blocks, these little boxes. However, Simulink does more than just this. Okay. So that's one thing we need to learn in this lecture, which is obviously going to continue next week. One is how to build a block diagram out of a system, something we have done. We have just done. The other thing we need to learn is once you have a block diagram, how do you get the transfer function? How do you reduce this block diagram to a single box with the input and the output and the transfer function written inside that little box? For that, we'll have to learn a few rules. Okay. One is when you have a serial connection. So when you have two blocks connected in series, the equivalent block diagram, so instead of, if you want to have one instead of two, will be this. You just multiply those two individual transfer functions. So this is equivalent to this. We'll see how relevant it becomes later on. So when you have these two blocks, you multiply what is within those two boxes. Rule number 2, this is called a parallel configuration, parallel connection. Parallel connection means that two blocks have the same input. So if this was X, this was also X over here. So they have the same input. They share the input. But the outputs are either added together or one output is subtracted from the other. So you have plus minus here. Again, summation point here. This configuration can be replaced by a single block where you have a sum or the difference of the previous two transfer functions. So G1 plus minus G2, depending on whether you have plus or minus over here. Third rule, the third configuration is called a feedback loop. It's a bit more complicated to explain in words, but again, you have two blocks, G1 and G2. The output of the first block is at the same time the input into the second block. The output of the second block is added or subtracted from the input into the whole system. And the result of that summation or subtraction is the input into the first block. This is called a feedback loop, a very important configuration for the rest of the course. The equivalent transfer function, so if you want the whole configuration to be expressed in a single block, single transfer function, is this. G1, that is the transfer function of the main branch. G2 is the transfer function of the feedback branch. So the equivalent is G1 over 1 minus plus G1, G2. So So if you have plus minus, over here you have minus plus. I will derive some equations, these three equations, in front of you, in front of the camera, but let's just mention the other two rules. So if this is a part of a much bigger block diagram, okay? So you have a block with transfer function G1, and then you have this signal taken to wherever, to another part of the block diagram. But for whatever reasons, you want this junction to be moved downstream, so this signal after G1 needs to be taken into the rest of the block diagram. You can do it, so you simply move it over there, but you have to multiply your new signal by 1 over G1. In which case, this signal here is the same as this signal here. Okay? So whatever you had, if you had x, this is G1 times x. Now this is G1 times x divided by G1, which means x again. A completely opposite case. So you have this part of the block diagram that you need to change. So you want this junction to move upstream, if that's the right term. So you want to take the signal before G1. You can do it, but you have to insert this transfer function G1 once again. Because if this is x and this is y as well. Over here, this has to remain y. If this is x, x times G1 will be y. So there will be different situations, as you are going to see, different block diagrams, different configurations. So you will have to apply different rules to simplify the block diagram and get one transfer function. Let me just quickly prove these 5 rules. Rule 1, if this is G1 and this is G2, let's call these signals, these variables, x, y, and z. Now, G1 in the S domain, okay, equals to y of s over x of s. G2 equals z of s over y of s. We agree with this. But we want to find z over x, the transfer function of the whole system. That will be equal to y over x times z over y. Okay? So you all agree that this is the same as this. But now, this is G1. This is G2. Okay. So that's the first rule, if you remember what we had earlier on the screen. This is why a serial connection of 2 blocks results in the product of those 2 blocks, or the transfer functions of those 2 blocks. Rule number 2. Parallel, some call it feed forward. Let's stay with parallel to x. So this is x as well. Y, z. Plus or minus. Now we are running out of letters. Let's call this u. Again, by definition, G1 is y of x, y of s over x of s. G2 is z of s over x of s. And we also know that y of s plus minus rather, z of s equals u of s. So u is not a step function in this case. U is just a function, just the output. Okay, what we want is u of s over x of s. That will be the transfer function of the whole configuration. Okay. Instead of u, I'm going to write y plus minus z. So I have y of s over x of s plus minus z of s over x of s. Okay. Y over s is g1 plus minus z over x is g2. Oh, yes, sir. Okay. You put your signs next to the arrow the signs apply to. So if there is no sign here, that means plus. So y comes into summation with the plus sign. But z may come with either as plus or minus. I'm doing both cases instead of deriving two separate cases for a plus and then for a minus. If that, well, it can, but then we'll have plus and minus here. But if both come as a minus, that is also summation. But just the full summation will have just a minus sign in front. Okay, if you have minus a minus b, it is the same as minus a plus b. So effectively, we have ordinary summation, and just we put a minus sign in front of everything. So that's why we are not covering cases where both are negative. So they are either both of the, let me put it this way. Both signals are either of the same side or same sign, or one of them has an opposite sign. The opposite sign. Okay, and the third one, once again, if this is x, let's call this E. G1, we'll call this Y. G2, again, and this signal will be Z. So this one, again, can be positive or negative. So therefore, we have a positive or negative feedback loop. Okay, now let's define what G1 is. It is Y of S over E of S. E stands for error, but we'll see later why this is an error. So Y over E. G2, okay, what is the transfer function G2 equal to? Sorry? That exactly. I'm asking this question because in this case, the signal flows from right to left. So you have to be careful. Always watch the direction of the arrows before you decide what is the input, what is the output. It's very easy to say input is what's on the left and output is what's on the right. In this case, it's the opposite. This is the input. This is the output. If you find this obvious, then I apologize, it's good. But just, I know that it's easy to make a mistake like that. So output is Z. Input is Y. Very good. And what else can we find? That E of S equals X of S plus minus Z of S. And what we want to find is Y of S over X of S. This will take a little bit longer than the previous two. I hope we'll get there. Okay. Where do we start? Maybe from the third one. Okay, E of S equals X of S plus minus Z of S. But over here, E of S is also equal to what? Y of S over G1 of S. Okay. So I'm rewriting this equation now. So a lot of jumping back and forth. So Y of S over G1 of S equals to, I want to keep X. I also want to do something with Z. So plus minus. Z I will express from the second equation. So Z is now equal to G2 of S Y of S. Okay, I can see. So okay, it's actually better this way. Okay, apart from I'm now having trouble showing the whole sheet. Okay. Okay, so once again, so instead of E, I'm writing Y of S over G1 of S. I'm keeping X, and now instead of Z, I'm bringing this expression over here. Right, now I want to group the terms with Y on one side and the terms with X on the other side. So I will have Y of S brackets 1 over G1, apologies, 1 over G1 of S. Now if this was plus minus, now we'll have minus plus G2 of S equals to X of S. Okay. And finally, we want Y over X. So Y over X will be equal to 1 over the whole thing here. 1 plus 1 over G1 of S minus plus G2 of S. Which now becomes, if we multiply by G1, we will have G1 of S over 1 minus plus G1, G2, everything is a function of S. So this is, if you still have your lecture notes open, this is what you have on the right-hand side as the equivalent transfer function to the original feedback loop, positive or negative. So you have positive feedback loop. If you have plus sign here, you have minus here, and vice versa. If you have minus, you will have plus. Okay, so these 3 rules, or 5 rules, are not given in the exam sheet because we believe, well, I believe in 2 things. First, these derivations are so simple that you can do it quickly. B, you will do so many examples for the rest of this course that you will remember them anyway, even if you don't want to. So I'm kind of contradicting what I said earlier. I don't want you to memorize things, especially not equations, but you will memorize these even if you don't want to. You know, I did when I was a student very quickly. So if I could, everyone can. Okay. All right, back to our spring mass damper system. So now we know the rules. Now we can simplify this block diagram and obtain the transfer function. Okay. So the first thing to do is apply rule 1, which is the multiplication of these 2 blocks. That is kind of easy. So it's not, well, actually, what I did here, again, I blame someone else, my predecessor. He jumped maybe 3 or 4 very important steps. So yeah, so you simply get here. So again, I'll switch my camera again and go step by step. But we are starting from this, okay, from this block diagram. Right, so let's rewrite as it is. Fi. Okay. These 2 signals are negative. Over here, it's ms. I'll write in lowercase, so in time domain terms. So mx double dot. Then we have 1 over m. So this is x double dot. Then we have 2 integrations. One integration, another integration. After the first integration, it is x dot. After the second one, it is x, the actual output of the system. Here we have what? Kx, and here we have Cx dot. So for that, I'm taking x, multiplying by k. So I have kx over here. Down here, I will take x dot and multiply by c in order to get cx dot. So this is the complete block diagram. First thing I want to do is change this part a little bit. I'm going to rewrite, or redraw rather, this part like this. I will still have Fi. I still have this minus here. But now I'm going to do this. And that will give me mx double dot. I'm not drawing the rest I keep the same. So instead of a summation with 3 signals coming in, I break it, so I have 2 separate summations. Do you agree that these 2 things are the same? Just the red circled parts of the block diagram. If you don't, just remember this. If you have, once again, if you have A minus B minus C, that is the same as A minus B minus C. And that's really what I've done here. Yes? Oh, that means that whatever signal you have here, it comes into the summation with a negative sign. which effectively means subtraction. So back here, fi comes as fi, with a plus sign. But kx comes with a negative sign, because it's in the actual equation you have minus. So you have fi minus kx. Cx dot comes with a negative sign, because in that equation you also have minus Cx dot. And all that equals to mx double dot. So this minus this minus this. So the red part here still shows the system. It still contains all information about the system we started with. So the minus sign just means the particular signal along that line comes as a negative, as the opposite sign, with the opposite sign. Yes? Well, this circle here is this. Fi minus b, a minus b minus c. Okay, let me rewrite it like this. Fi minus kx minus cx dot. This one, I'm just saying I want to do this first, fi minus kx. And then I'll do minus cx dot. That's all I've done here. So this is still kx. I haven't changed that. This is still cx dot. I haven't changed that neither. Okay. But this is very important, because this will help me simplify the block diagram eventually. Okay. So now, next thing I'm going to do is multiply these two. Apply rule 1 on these two blocks here. Okay. Thank you. Sorry. Yeah. Just don't know how to zoom out. Okay. So I'm going to call this rule 1. So I'm going to apply the product rule. Multiply these two. So now let me draw the new, a bit modified version of the block diagram. So fi, can you see? Yeah, okay. Then we have this minus. Then we have another summation. We have this minus. So we keep that. Now, those two boxes are multiplied, so I have 1 over ms. Then again, I have 1 over s. And now I have x. Here I have k. Here I have c. So those things haven't changed. Now, next step. Can anyone identify what would be the softest target now? A feedback loop here. So we can replace this feedback loop with a single box, with a single block. So we are applying G1 over 1 plus, because of the minus sign, G1, G2. So, Fi, this is the same, but here, G1 is 1 over ms. Then 1 plus G1, G2, C over ms. We haven't touched this, so we still have x, we still have k here.
Okay. And I believe that's the picture, the next picture you have in the lecture notes. That's correct. Okay, from now on we can move back to the lecture notes. What will be the next step? Sorry if you're still catching up. I'm happy with that. Okay. So I hope now you see what will be the next two steps to do. Of course, we are going to simplify this. This is too clumsy, so we are going to create a nice, ratio of two polynomials to make it simpler. And then once we do that, we will multiply by 1 over s. So we have G1, G2. Okay? And then after that, we'll apply another negative feedback loop. Okay. So the feedback branch does not always go from underneath the main branch. Sometimes it goes above, like in this case. But it is still a feedback loop. Okay, so this would be the main branch, this would be the feedback branch. So we can now turn on the computer again. So this is where we left off. So now we are multiplying this. First simplifying this will give us 1 over ms plus c times s. Okay, sorry, no s. So 1 over ms plus c, and then times this 1 over s will give us this s over here. This feedback loop, as I said, is the same as having a feedback loop running underneath. So it is the same thing. But now we can clearly recognize it as a negative feedback loop, so we apply that rule once again. This would be G1. Okay, so therefore 1 over S ms plus C over 1 plus, because of the minus sign here, so it is 1 plus K times G1. So K over S ms plus C. When you rearrange this mess you have inside the box, you're going to have a nice expression here. So your transfer function, effectively, Fi is the input, x is the output. What you have here is the transfer function. Okay. Or you can even make it more recognizable, get rid of the brackets, so you have ms squared plus cs plus k, as we had earlier when we were dealing with this. So just briefly, now we are going to make a little digression from the block diagrams and see once again what we can do with this transfer function. Once we have the transfer function, we can apply any input you want and analyze the output. So if you apply a step function of magnitude f, so not necessarily a unit step, a step function of magnitude f, that means f over s. That means the output will be equal input times transfer function, so you have f over ms, s squared plus c over ms plus k over m. Why did we take m out? Because we want our denominator to be normalized. The coefficient with the highest term has to be 1 because we want to use the tables, Laplace transform tables. Remember we said that in your tables, all expressions on the right-hand side are normalized. All expressions in the S domain are normalized. But if you look into the tables, I will be stubborn using case 22. I know you prefer 20. You see that these two coefficients, the last coefficient in the denominator and the coefficient in the numerator, the constant in the numerator, have to be the same. So if I have k over m here, or here, I have to have k over m in the numerator as well. So therefore, I will take k outside here. So I have f over k, so I can have k over m. Now I can compare these coefficients with the coefficients in the Laplace transform table. So the last one is omega n squared, but the second one is 2 psi omega n. So k over m is omega n squared, or omega n is square root of k over m. Then c over m equals to 2 psi omega n, so psi becomes equal to c over 2 square root km. And these coefficients have their special names. Omega n is called the natural frequency of the system, a very important property. But psi is even more important, especially for this course. Psi is even more important. It is called damping coefficient or damping ratio of the system. So if you use the tables, check now what is on the right-hand side, and just substitute the expression for omega n and psi wherever you have them. And that's where you get the time domain expression for the output. So first you have a constant, and in brackets you have 1 plus another constant, decaying exponential times a sine function. This will be the frequency times time, and this will be a phase shift. And there are a few things we can notice here. First, our system is going to oscillate. So if you think about the mass in a spring, you apply a force downwards, the whole thing will oscillate, which is something you expect, right? But second, the amplitude of the sine function is not constant. The amplitude is decreasing because you have an exponential with a negative argument. So that means the oscillations are going to settle. When time becomes long enough, this amplitude will be 0. So we have damped oscillations. And finally, when those oscillations settle, where are they going to settle? When this is 0, all you're going to end up with is f over k times 1, f over k, which is something you kind of knew. Had you applied this final value theorem, you would have got f over k anyway. Final value theorem gives you the final value, or something we also call steady state value. So steady state is once the oscillations are gone, once we don't have oscillations anymore. Okay. Any questions, guys? We'll continue with block diagrams next week, obviously, but if you have any questions now, please ask. Otherwise, you can start working. You're most welcome to work on previous sets, 1, 2, 3 if you want, but you can also try to do some of block diagrams. You will find some of them difficult because we haven't finished the lecture, but at least you can give it a go. Questions from past sets are also welcome. Thank you. Okay, if you don't have questions, the tutor's already coming, so we can start. Also, please leave every third row empty, which is only critical here and there. The rest is not very difficult. We want to be able to reach you guys. Okay, room controls. Oh, it's still running for 5 minutes. Oh, you do have a question. I thought you would come yesterday after class, but thanks for not coming. I was really busy. After Aero class, I thought you would come to ask
question?
No.
I was really busy preparing it.
I only come for consultation hours. So, what is this cycle? What is this? What does this mean? What do you call this?
What was that?
Yeah, the M.
M is mass.
I mean this cycle.
Oh, they are summations. So you are summing two or more signals together.
Okay.
But it could be subtraction as well. So if you put a minus next to one of the signals, that means it will be this minus this.
Okay.
It is just a graphical representation of algebra.
Okay. And right here, we got x times k
Yeah.
to
Is
get
K is
kx.
KX. Yeah.
Why don't we get from opposite direction, like kx times 1 on k to get x?
Well, but you can't because you don't have KX. When you remember, we started with this part only. Okay.
Yeah.
So, but here, KX is coming this way. It's not an output. It is an input into this summation.
Okay.
Okay. So, and the only output from the summation is mx double dot. So you use this to create x, doing this, and this.
All right. Another question is, we write here, we write mx double dot
Yes.
instead of ms squared x.
Yeah, it's the same thing. Same thing.
Which one do we prefer?
Which one? I know what you prefer.
I prefer the previous one.
Okay, then that's what you write.
Okay.
I prefer this. I write that.
And right here, why don't we just directly write f on k equals this instead of calculating x?
Sorry, I think that's a mystery. No, this is wrong. This will be f on x. No, it's actually completely wrong. It should be x on f. Sorry. Okay. Sorry, x off. No. Just, I have to delete one equal sign. No, just delete equal sign. So it's f on k times this, which is the same as f on equal sign should be deleted.
Should be a dot.
Should be dot, should be times. Like this. It's just rewriting this expression. So it should be equal. So it should be no equal sign.
Yeah.
I have to remember this. Delete equal.
Okay. Right. Thank you.
That's
เ
啊。
Block diagrams. He said that because he's somehow
block diagram.
progressing faster, maybe block diagram.
Artists keep the sensory.
Oh yeah.
4 a.m. You have to work so
doing some
hard.
project because we want to shoot something today. It's crazy. Yeah, and the two other colleges we are making something to label the lead, copy lead automatically.
Coffee?
Copy lead. And usually somebody coming order something because there is a product called the Smart Table. It's an app. So the order will go through the app, and the app will send to the label printer. And automatically label is on there. How's your research? Any progress?
Progress is stuck with time, like in a sense I have really I'm putting lot of time into designing and all that stuff. So I'm finding it really hectic now. I have to find somehow I have to manage on weekends now. Otherwise I'm dead.
So you need to publish.
Yeah, I'm working on a paper. The thing is I need to finish it quickly and then start the next topic. To finish that quickly now, and it's pending since a long time. Like I'm already delayed it for 2 months or something.
Delayed? Why?
Like some update some results, and like the results were not proper, so I had to work on that. So because of that, things got delayed, and
It's very common. Sometimes it's delayed for how many years. It's very common. This is research.
it is so unpredictable. The biggest problem.
Sometimes you cannot like wait till the result becomes very good and then you publish. You have to if you have idea, final result because time is very short.
And without publication,
It's not they could predict.
like in a sense, like in the APR, they will just the main point they will check is you have how many publications you have.
But I have never hear anybody fail in the exam. And several students in my office graduated without any publication. So it depends on your supervisor, I think.
Even publishing with my supervisor is really difficult. Like in a sense, he will have very strict standards. Like he will keep on giving revising and making it more tougher for him.
Okay. So your advisor is professor?
Yeah, he became a professor last year from
Good thing and bad thing. Did you start to like
I'm going to apply for chemistry.
yeah. Okay. When?
Maybe
Start
this
it?
week.
Finish this year.
And then I got my doctorate. Getting 10 points.
10 points. Or 2 points means. Or 3 means like 7 points.
Actually, I missed 20 points.
But why constant function is it in S equals 0?
Yeah,
Is
S
it?
is 0.
S equals 0?
Yeah, it's
But why?
0 hertz frequency.
Yeah, because it's S
In the
equals
transfer
sigma
function.
plus j omega. I'm setting the entire thing as 0, so omega equals 0 as well. So you have
So it's the gain.
so it's like input of a
Yeah, this
response to
game
a
is
0.
when it goes to infinity.
Yeah, but I can find it just by setting s equals 0. Right? It's also when t goes to infinity when the input's a unit step, not impulse.
Impressive.
Okay, I did it wrong this morning.
Sorry?
I did it wrong this morning. Because
You
I
got
thought
your test?
yeah, because I thought it was impulse, but then it sounded wrong. I was like, why is my DC getting 0? But
Okay.
Yeah, because we
I went
only
through the
have
test
one
today.
S, yeah.
I went through the test today, but I did that part wrong.
Oh, the DC gain.
Yeah.
DC gain.
So I did that part wrong.
It's t equals to infinity.
Yeah.
T
And,
goes to infinity.
SFS is in the limit of 0, but because you have unity impulse input, then that S is the S of input. you
Oh,
can-
okay, okay.
这个是个
Or it's testing the performance of the system while you are given an input of a step
这
function.
个
Yes.
这个没有这个，应该是这个出来的。
But why?
哦，这边是吧？
It's all, anyway, it's a definition. Or it can reflect some performance of the system.
Yeah, you can see the system is stable or unstable.
Ah,
Excuse me, do you have the answer sheet?
apparently I don't have.
But, thank you. One C.
What is your cost? What is your cost name?
One C.
I need a test you take. You test you too. Because you just now you told me you make mistakes this morning.
Oh no, I mean like I did their test in the tutorial. The test they did last night, I did it in the tutorial.
Ah, what is the cost?
This course,
This course.
yeah, they had a test last night.
You wrote this course?
No, these guys had a test yesterday night,
Oh yeah.
and I did it in the tutorial today. But I did it wrong.
Okay. Sorry. By the way, the arrow, because we don't have arrow actually initial for this question. Should be this way or this way? This way. You see this way from the answer.
No, he has set these two as parallel.
Parallel. If parallel should be plus, right? Like this block plus this block.
Yeah, but if it is negative, then I mean you can add these two again, because if it is negative, then if it is negative, then it is 1 over 1 plus GH. If it is positive, then it is 1 over 1 minus
But
GH.
this is parallel, not a feedback, right?
No, it's a feedback.
It's, this one is not feedback.
No, this is feedback to this. This is I mean, apparently as he has solved it, this has been a feedback to this, because now we have G over 1 plus GH.
So should be, the signal should be like this. And we should have a signal here, right? Because we have a signal here, we have an arrow here. The question, you see? But here you also get an arrow.
Yeah, but this is a feedback to this loop.
It's just the response to our step function.
I think it's a feedback. I don't think it's a feedback. A feedback is always like this way and this way.
Yeah.
I think if we don't consider about this point, then it's a feedback, right? And like you can use this one and 1 over 1 plus this one. Like we ignore this arrow.
So it's equal across all
We always look at this as a feedback, but the rationality behind it.
There is no arrow for this one, so I don't know where the arrow is.
Arrow.
Yeah, there is no arrow.
They are all coming in here. Two are positive, one is negative.
Okay, I got that. I got that. Actually, we don't have arrows. It's this one and this one.
Because it's not a variable, it's not an S rate. I completely forgot that. So I was like, there is a transfer function, and S times G of S, set S is 0, and you get C is 8.
No, not SG.
It's just G of S. Yeah. So I fucked that up, and I was like, yeah, my DC game's 0. That doesn't make sense.
And none of them corrected you?
They did what?
Oh, really? I've got a couple like that are quite like on the ball. So like if I fuck up, they usually pretty quick to pick up on it. They're like, you mean this? I'm like, oh yeah.
No, those are my fault. They just correct my numbers.
Oh,
Last stuff on it.
yeah. I love it.
They don't get a really good basis. They don't even teach you linear algebra.
No.
It's actually really, really
1, 2, 3. I think I did 4, 5, 4, 7. I think, yeah, I skipped 8. I did 9 and 10 as well.
That's the one asking me the question for the that's why. This one. Yeah. And then the last question.
Yeah, that was question 2 on the exam.
So you already got that. You already got the solution for that.
Well, no, because for that it was only doing the the question it had, you know, time constant, then other stuff as well. Like those
Yeah, because the demand. Oh, okay. I got that.
like part A was this, but there's part B, C,
I
D.
can do that because they always focus on the first 3 sites. So is there any time constant?
Well, but I'm pretty sure it's already modeled because up to 4 and 3. Oh. Like time constant is what, somewhere in between 2 to 3 and 4. Because it was lectures up to lectures 5 or 5. Because 5 is in.
Anyway, the question over here. So this is transfunction because this full exam is a
Yeah.
this full calculation the question this one is for the function. And then if the input f is the impulse function.
Yeah.
So why the model value?
Oh, the last question.
Yeah.
It's like, why is it only
Because for the input is 1, so Laplace should be 1 like this. So for the f is equal to 1 input, and then 1 times f times t over f equal to just 1 times this one. So we just assume a on the top and then b for the c and then plus at a is d. So 3 constant here. So this one, why this model, yeah. So the factor is a 1 over yeah, so
It's upon ds plus b.
inverse product is e minus some a over b, e minus d over b times t. Why this one is a constant? Why this model is valid?
Is it at the start he said that we always have to make assumptions, and then he mentioned this example like if you put anything more than the voltage is like constant, not voltage, velocity is not constant anymore, so the picture is
Second order system for that. You'd get an oscillating system if you would apply unit step.
Yeah.
So can you have negative temperature? Would you expect it to oscillate?
Something to look for you. So the U over you are right. V-bend, but
Well,
find
you
the one.
imagine, like, if you push down on a brake, what's going to happen? What's going to happen to a wheel if you squeeze it?
I think assume nothing happens.
Well, yeah, if you make that assumption, then the system works. But,
And maybe some,
but if you squeeze it, then the velocity is not going to change that much. But if you like hold it down, it's going to slow down. Right?
do you think that exam think about it?
I think that's one of the things. You've got, you're assuming that all of them are going to
Yeah. Fine. Okay, thank you.
这个
对，3。好，question 7。这个题啊，在哪儿？对呀。
rearrange it and then put it another vector on, no rearrange.
它果然是做7 drop， 7 drop，
不然哪一点？
7 drop 1 0。
就有一个项要，如果2项的话，有一项衰减比较快那一项要忽略掉。
我想的就是当时你想的是正负衰减这么走，对吧？就可以找一个那个，比如说1/4周期的，但是1/4周期就是跟这个结构是不一样的。
它是不是有两个量？几个
我们找4分之1周期吗？不应该是找那个。
这么走的话，
就是一般都是球，它是球导。
是啊，physically是球导，但